So the rule here is that if more males have the trait, then it is X-linked. What that means is that it is on the X chromosome. X-linked means it's on the X chromosome. When something's linked to a gene, a chromosome, that means it's on that chromosome. All right. Now, believe it or not, this is really important because I could easily see them asking you a question in OST on this. And you're gonna get your next checkpoint's gonna be your genetic checkpoint. All right, so let's take a look at this. How many X's does the male have? 1. It's an X, Y, correct? How many X's does the female have? 2 X's, correct. Where did this son, this is second generation, this is first generation, this is second generation. Where did this son get, what did that father from the first generation give this son? The Y or the X? The Y. And it gave this son a Y too. The mom, I'm going to do a different color for mom's X's. The mom gave an X to the daughter and to the sons, and dad only gave an X to the daughter. Okay? Now, if this were X-linked recessive, that means the gene is on the X. And recessive means it's a little a. So mom does not have the disease, so she's big A, little a. She has one of each. Correct? Dad doesn't have the disease, so he has a normal X. Even if dad had, let's go look at, let's say dad had the disease and was little a. Let's look at that example first. So dad has the disease. He has the trait. Mom doesn't, but she's a carrier. What are the odds that dad will give the disease to his boys? 0. Why? Because they don't get an X from dad. They only get it from mom. So, mom, what are the odds that the boys have an X little a? What are the odds that these two boys have X little a? What is it? 50%, correct. 50% chance. Why? Because mom is either going to give him a big A or a little a. One or the other. It's a 50%, 1 out of 2, 50%. Do you see that? Don't just nod. Look and think. What are the odds that the mom will give, that dad, we know that dad's definitely going to give his daughter a little a. What are the odds that this daughter has the disease? 50%, correct. And of course, it's 50% here. So in this case, they're all pretty much equal, correct? All right. So now let's take a look at another example. Same situation, same recessive, but let's say dad is dominant and mom has the trait. What if dad does not have the trait, but mom does, because she's homozygous recessive? What happens now? Let's take a look at the data. Is dad going to give this guy a dominant gene? Dad will give X big A to this son? No, why not? Because they give the Y. Same with this one. So these boys, what are the only thing that mom can give them? X what? Little a. So these two have the disease. For sure. 100% chance to have the disease. What about the daughter? She's going to get a X little a from mom for sure. Correct? What are the odds that they have the disease? Look at it. Think about it. They get an X little a from mom. What are they getting from dad? So what are the odds that the females can have the disease? Say what? 0 is correct. This is 0% chance. Why? Because dad can only give what? X big A. As soon as you get the big A, you show that trait. In this case, that means no disease. Why is it not showing up there? I don't understand. Oh. So, that explains why anytime you have a pedigree that shows mostly males have it, it's because it generally is because it's X-linked. I don't know why this thing is acting up this way. Always depends on the time of day, the moon's phase, or what, but all right. So you get 100% chance that the males will have it, 0% chance female. When you add it all up, X-linked recessives are mostly found in males when you look at the pedigree. Shh. So when you have a pedigree, if it's not filled in, could someone shut that door? That means that it does not have the trait. The trait does not have to be a disease. Is that clear? Often it is, but it doesn't have to be blue eyes, could be tall, could be whatever. But they don't have the trait. So what you're looking at when you see a pedigree is the phenotype. A pedigree is looking at phenotype. So you don't see the trait. If it's filled in, that means you do see the trait. You do see it. They have the phenotype. Is that clear? That does not mean it's dominant. What that means, or recessive, what that means is that you see it. What are the two possibilities? Well, you see it or you don't. And so if you see it, it could be little a, and therefore a recessive gene. Or it could be big A, little a, therefore it's a dominantly inherited trait. We just don't know based on just two people getting together. Yeah.
So if someone is to be a carrier of a trait, that does not always mean that they phenotypically show it?
That's correct. That's the definition of carrier. The definition is that they have the gene, the allele, but they don't show the trait. The only way you can do that is what? What's the only way to do that? So what is the only way for a gene not, hear me clearly, what is the only way for you to have a gene and not show it? If that gene is recessive. If it's homozygous recessive, you see it. So it has to be recessive. And you have to be heterozygous. So let me quickly make two different pedigrees really quickly. So we have here this going on, and maybe no one in the next generation shows up. You understand that this is the parental generation, the P generation, and this is F1, the first familiar generation, okay? And then there's going to be another generation that's coming. Maybe this girl dies. so dies at birth or whatever. It happens. And then you get this going on. All right, so now based on this, could we tell what kind of inheritance is going on in this pedigree? Yes. Yes, we can. So let's go back and figure this out. This person had the disease. This person did not have the disease or trait or whatever. None of their children, 1, 2, or 3, I'm going to label them. 1, 2, and 3. Two died. 1 and 3 don't have the trait. Is that correct? You read that with me? Are you agreeing that that's what we see? Okay. This one has a baby, right? That has the trait. So this one had it. This one has it. In between, nobody had it. This generation didn't have it. What's the only way that could happen? Yeah. If it's recessive. If it's recessive. Because the only way it could skip a generation is if it's recessive. Because if you have the dominant gene, then it's going to show up. If it were dominant and you had it, it'd show up. So the only way for these two to give it to their child and them not have it is if the gene is recessive. Do you all agree on that? Yes.
Yeah. So for the first generation, for the woman, would that mean that she would most likely be homozygous dominant?
You're talking about this person?
Yeah.
We don't know yet. Let's talk. Let's work that out. We're only going by what we know. So we know it's recessive. We all understand how we got recessive. How did we get it was recessive? Because it skipped a generation. That's it. That's one main rule. If it skips a generation, it's recessive. Boom. Drop the mic. All right. That's good news. Yeah.
Like in the case of, what if it's like there's a heterozygous person and
Well, let's do let's do it. Let's do it. Let's go ahead and do it. So that means that this person here is little a, little a. We know that. We know this person here is little a, little a. That means that this male gave to each of his children at least one little a. We know that happened, correct? What do we know? What do we know then? Okay, I'm going to have to use a different color because it looks like it's all going to be jumbled up. We know that this person got a little a. Let me go ahead and put it in the box. We know it has a little a. We know this person has a little a. How do we know that? Because what did the father have to give? No, the father could only give what? 2 little a's. That's what the father had to give. That's the only thing the father can give. So we know these recessives, they give us a lot of information. We know that they can only give you can only give what you have. Why is this not letting me? Oh my God. This thing's jamming up. I'm sorry. Give me a second. So this individual's little a, little a. We know that. He only can give little a. So all his children had at least one little a. We all agree with that? None of them showed the trait. So what must the other parent have given them? Must have given them a big A. And we know mom had to have at least one big A. What about the other one? We don't know. Could be anything. Could be a big A. She could be double big A, or she could be big A, little a. Correct? But we know she has at least one little a. We know, what do we know about this mom here? What is it? Big A, little a. How do you know she has big A, little a? Because one of their children had two little A's. That means you got one little A from each parent. So they both had to have a little A. I hope you're paying attention because you have to use this logic every time you see a pedigree. What do we know about this parent over here? This female over here.
She has to be either
What's
heterozygous.
we don't know. We know she's a big A, but we just don't know what the second one is. We know she has a big A because you don't see the recessive trait. What about, let's go back. What do we know something about this one? What do we know about that one? It's definitely homozygous recessive, which means its parents are big A and little a. Which means that, and we know this parent is at least big A. We don't know the other one. We know that we know these are all big A, but that's all we know about these. We don't know the second one. So that's all we know about every person on that pedigree. Yeah.
So just because it's heterozygous doesn't mean that it's always shown?
That's right.
Okay.
Well, what you know is when someone said, all you can tell is if someone has the dominant trait.
Okay.
Or does someone have the recessive? First, you have to figure out, is it dominant or recessive?
Yeah.
If it's recessive, it's going to if it skips a generation, it tells you 100% that's a recessive trait.
Yeah.
There's no doubt. Now, there's another tendency that you have to know that you're going to have to use. When a gene is on a chromosome, we say that the genes are linked. When a gene is found, let's say you have a gene A is on the X chromosome, then we say it's X-linked. So when you see something like this, this is an extreme version, but when you see something like this and you see that mostly what do you notice about this? Mostly males have it, right? When mostly males have it, have the trait, then we say it's X-linked. The gene is on the X chromosome. Why do we say that? Women have two X's. And women most of the time, men have a higher chance of getting the X-linked trait. Some women might have it, get bad luck, but especially if it's X-linked. Is this recessive or dominant? Is this recessive or dominant? Look at the chart. It's recessive. It skipped a generation. Done. This is X-linked recessive. So I have a video I'm going to post for you. You have these activities. Get them done for homework. I kind of want you just to do that rather than do anything else. I had a case study for you, but I think that's too much. Just do these case studies. Watch the video that I'll post. That'll be your asynchronous activity. Work in Zoom groups to get your international studies things done, and get ready for Thursday's. Are you hearing me? Yeah. Thursday's test. You're gonna have a pre-test tomorrow. I will post it. I'll give you instructions. All you gotta do is log on to your lockdown browser and take the test. That's your Hey. Okay, so let's take a look then at what we have here. If we look at the squares that are used to indicate males, that tells you exactly what you need to know to be able to analyze this. Also, remember you have in your assignment in Schoology, you have further notes and details. So when you look at this and it says questions 1 through 9, use a pedigree chart and some labels to be some of the labels may be used more than once, right? And you'll see this says in a pedigree trait, it can be dominant or recessive. So remember that, all right? And a majority of harmful genetic conditions are only seen in an individual that's homozygous recessive. The majority, but not all. So remember that. That says majority. It doesn't say all. So even though that's true, don't get in the habit of assuming that something is recessive because it's dangerous. Example conditions cause recessive alleles. Cystic fibrosis is an example. All right, and the disease, a disease of a secretory glands, blah blah blah. You can read the rest of this. There are some conditions, as I said earlier, don't assume all that are dominant alleles, and therefore it expresses homozygous dominant or heterozygous individuals. And some of those conditions, as you see here, are polydactyly, the presence of an extra fingers, dwarfism, this type of dwarfism, neurofibromatosis, hypercholesterolemia, which can all be dangerous, by the way, or at least the neurofibromatosis and the hypercholesterolemia. All right, so let's go ahead and answer the questions. So number 1, which one's male? Well, this is square. Which is female? The circle. A marriage is a line, a horizontal line. A person has expressed a trait as someone is filled in, right? Or, either one, or, right? A person does not express a trait, well, that's this or this, right? Either unfilled, right? A connection between parents. Oh, I see. There's letters here, aren't there? Yeah, I guess I should be more careful when I read. So, male would be C. Female would be A. A marriage would be B. A person expresses a trait would be A. A person who does not express a trait would be C. A connection between parents and offspring would be D. How many generations are shown in this chart? This is the first generation. This is the second generation. And this is the third generation. So there's 3. What is the most likely genotype of individual A? And so I look at this and I see that there is no skip generation. You have a female that has it here. There's a female and male that have it here. And then I see there's a male and females that have it here. So there is no skipping a generation. So it's likely a dominant phenotype or a dominant gene. I see also that there's in fact, there's more females than males have it, so it's not X-linked. So it's likely an autosomal, that means not X-linked, autosomal dominant inheritance, okay? So what's the most genotype individual A? Well, if A were big A, then all their children would have it. So this child and this male child could not have this if this were a dominant allele and the parent, and this was homozygous dominant. So it couldn't happen. They have to be, if it's a dominant inheritance pattern, then she'd have to be big A little a, and that's because that would make this male little a, this female big A little a, It's not X-linked, so that means that this female could be little a, little a. In other words, one little a could come from this mother and one little a could come from this father. This one here in the center, oh, I'm sorry, this is supposed to be dominant, right? I'm writing it for recessive. So this would have a big A and it have a little a. This could get two little a's, the big A here coming from the mother and the little a from the father. This could be two little a's, one little a from mom and one little a from dad. This one could be, again, big A, little a. And this one could be little a, each getting one little a from each parent. So that's all fine. And of course, this is also little a, little a. This is supported by the fact that none of their children have the disease at all, and they're both recessive. Where here you have a if this were still true, and this is heterozygous, this homozygous recessive, then this explains how this one could end up little a, and this would be big A, little a, big A, little a. All these are little a, little a. Again, it just follows that from the idea that all the children get their genes from their parents. And this, of course, would have to be homozygous recessive, and this would be have to be heterozygote because it has to get a little a from dad because that's all dad has to give. And that would be the breakdown of all the genotypes on this chart. So A would be heterozygote, big A, little a. What is the most likely genotype of individual C? Well, that would have to be little a, little a. And how did I figure this out? I'm going to say it one more time. Number one, the number one part here, the most important part, there's no generation that's skipped. Every generation has it, so it's likely dominant. The boys don't, most of the individuals that have it are girls, not boys, or females, not males. And so, or men, or women, not men. And so you have to assume it's not X-linked. So when we look at this, dominant versus recessive, no carriers are not included in the with half-colored shapes. So they're telling you they did not fill in the half-colored shapes for any carriers, all right? So this could be a carrier, let's say. They're not telling you. So the dominant form of the normal, they're telling you right now, right in the problem, that dominant is normal. That means it's not going to, the recessive form gives you the anemia. So which ones have the anemia? This is the anemia. It's recessive. It's Fanconi anemia. And so let's use little f for, and see, notice how I'm making a chart to help myself. Little f is going to give me Fanconi's anemia, and that's because it's recessive. So that should be filled in. So this one here is definitely little f. These are all little f. Because they have the trait, they all have Fanconi's anemia. So the next part of this process is they tell you that they're not indicating the ones that are carriers. They're telling you they're not going to include that information here. You have to figure it out. You have to fill it in. So if this is little f, then don't these two have to be carriers? Because don't they have to give the little f to their parents? And notice they skipped a generation. Even if they didn't tell you that it was recessive, or here they tell you it's recessive. Look, these two don't have it, and this one has it. So they skipped a generation, so this is definitely recessive. So it also means that each of these parents had to have a little f, because this female child, Carla, could not have two little f's if they didn't get one from each parent, which also means that each parent must have a big F because they don't have the disease. So both of these are carriers. If you were going to draw it the way you should draw it, then what you would expect to see is this square would be half filled, right? And this circle would be half filled, and they would be married. That's what it should be. But they're not doing that because this is a test problem. This is a problem they want you to solve. So moving forward, filling in the rest of these, you know that this parent, this Sam has a little f, and a big F because it doesn't have the disease, little f because Arlene had the disease, so she's little f, little f. Sandra married Tom, and both their children, Sandra, has to have a big A, and Alan and Daniel have to have, I'm sorry, I said big A. I'm just used to using A because it's easier. Has to have a big F. Daniel and Alan have to have a little f because Tom gave them a little f. They have to have a big F because they don't have the disease. But we don't know what Sandra's other gene is because we don't have enough data to really make a definitive decision. We know Wilma and Tom got 2 little f's. They got one from Arlene. Wilma and Tom got 2 little f's. And they got one from Arlene. Where'd the other one come from? It had to come from George. So George has to be big F, little f. Now, Alan has big F, little f, right? How do you know he got big F? Because Tom gave him a little f, and his mom gave him a big F, Sandra, so he doesn't have the disease. They had a baby called Christopher. They say Christopher got the big F from Alan, but they don't know what the other one is. And Tina, we're not sure either, except we know she has a big F. We just don't know what the other one is. Why can't we tell? Because we don't have enough data. The only time we really know that somebody has is the evidence from their ancestors or from their children that tells us something about what they have. So, moving forward, what is Arlene's genotype? As we just said, is little f, little f. What is George's genotype? Big F, little f. What are Anne and Michael's genotype? Anne is big F, little f, and so is Michael. What most likely is Sandra's genotype? Sandra is big F, and we're not sure what the other one is. Hey, come on in. You can take a seat. I'm here till 4:20. List 3 people from the chart other than George are most likely to be carriers. So George is definitely a carrier. Well, Michael, Ann are definitely carriers, and probably Sam. So Sam, Michael, and Ann. In fact, you can say for sure that Ann, Michael, and Sam are carriers. Why? They have to have a little f because their mom, Arlene, had 2 little f's. That's all she could give them. Sandra, we don't know anything about her past, so we can't really say. We know she has the big F. And we know Daniel and Alan are also carriers because Tom is little f, and that's all he can give them. All right, so that's how you figure out a pedigree chart. So here we have a disease, dominant recessive, okay? Here's a typical pedigree. Now here you see it's little n little. They tell you the recessive is normal protein, so the normal, they tell you in the problem, normal means it doesn't have it doesn't show up. Dominant in this case means it shows up and it's the disease. So if you see it, you're going to see the disease. So here we have one. It says one we know for sure is a big N. Let's just use N because they're using N everywhere else. All the rest of these we know are little n. Why do we know that? Because it's recessive. Normal is recessive. Notice I said normal is recessive. In this case, dominant is disease. So you really can't tell the difference. You really can't tell that it's a disease, therefore it's recessive. You can't do that. Even though a lot of times they are, sometimes they're not. And with the rest of these, we know that this is big N something. Now here, you see, you have these two are, look at your recessives. The recessives are always the key to genetic problems. Here's a recessive, homozygous recessive. Here's homozygous recessive. That means that these two got a little n from both parents. If you know that this parent had little n, big N, little m, n, you know this parent has to have big N, little n as well because 2 of their children had 2 little n's. You just don't know what this male has as a second letter because it could be heterozygote or it could be homozygous dominant. You can't tell because both his parents are heterozygote. You could do a Punnett square and figure it out, but that's where we're at. That's where we're at there. This parent, this child here, you know for sure is big N, little n. And why do you know this person is big N, little n? Because parent obviously has the disease and that's dominant. But then the father didn't have it, so it has to have a little n from dad, so it doesn't have it. And again, this person has heterozygote because one of its children or two of her children have little n, so she had to give a little n to them. So this female is definitely a big N, but also it's a little n because its dad could only give it a little n, and its mom, obviously it's diseased, so it has a big N. And that's how you figure these out. You look at what the parents had. You ask yourself, what did the parents give it? What could the parents have given it? What can you rule out? What do you know? You know the recessives. The recessives you can fill in easily. The dominants are a little more difficult. Is individual 1 most likely homozygous dominant or homozygous or heterozygous? We just answer that, heterozygous, and why? Because it's going to be heterozygous because it had children that were homozygous recessive, and that means it gave a little n, so it had to have a little n to give, so it has to be heterozygous. What is the genotype of 3? Individual 3 is little n. It's recessive because the normal protein is recessive. Can you be sure genotypes are affected siblings of number 3? Yes, for sure, because the only way to get normal, non-disease, is to be recessive, homozygous recessive.